completely different, as they say. But yeah, that was the idea. We went for the N in modeling. And we did a bit of design as well. So my job right now with this slide is just kind of to convince you that we have an interesting problem. And if you get lost at this slide, we're going to be out of work for the rest. So I'm going to take a little time on this. So in mathematics, yeah, people do it on chalkboards. They talk, they argue, they read books, they study their whole lives. That's not what goes on with computers. With computers, people program them, they build these formal models, which they may also argue about. Ultimately, the computer checks it using logic, right? So there's not a great way to model what really goes on if you find people at this chalkboard arguing about mathematics. Why do we care about that? Well, if you wanted to build a machine that would do mathematics, like machines can compose music, as we see, machines do other interesting things, generate stories, or read stories, or do tutorial sessions. But one that make a great AI for mathematics, like you could do for Go, you're going to need to get some data. And that data hopefully will come from the real world, in which it's this messy world in which people are talking and asking questions and arguing with each other. It's not this nice formal world which has been constructed as this kind of castle in the air by formalists. Nothing against formalists, but if you want to build mathematical AI, what you really need is representations of mathematics in which meaningful patterns can be found. So that's the problem I'm addressing now. And you could think of, your bog standard calculus textbook or whatever, something that I'd like to push into the computer. So that's the issue here. So let's break this down a little bit. In mathematics, you've got what we're calling a formal register, and that is where you talk about stuff, and you can transmit it into symbols and back, and there's nothing lost, okay? Every integer equals the sum of 4 squares. That's what that thing says also, and I think everyone who knows the symbols would say, yeah, they're equivalent statements. So nothing is lost, and here's a nice little quote, no reference is made to meaning. So no one says what these things mean inside of that formula. No one says, oh, I prefer M2 to M3, really, nothing like that. And I'll explain a little bit more about why I say trees give you the look and feel of the formal register. If you're a list programmer, you like trees. So I like trees too, but they're formal. I'm more interested today in this thing called the expository register. So where someone might say, next we will prove this theorem using an algebraic identity similar to the one we just used to prove the 2 squares theorem. So it gives you some kind of sense of context, how things relate to other things, and this is different from the one above. So let's break that statement down a little bit as well. So this is something from an architect, so this is where some of the design thinking comes in. Christopher Alexander says, cities are not trees. Why? There's a tree, there's your nice familiar tree. Why are cities not trees? Well, cities have these overlapping elements inside of them, right? They have, or hallway conversations, if you look at around the building. It's like intersection points, which were these kind of overlapping sets that don't sit nicely distinguished from all the other sets as you would get in this tree-like model. Okay? So this is an idea from architecture. Cities are not trees. The discussion I had about mathematical proofs is that, yeah, you can write down a mathematical proof as a tree. That's the formal pattern where the things aren't interacting with each other. But this messy world in which people argue and discuss, that's more like the picture on the left. But of course, cities could be imagined, just taking a little bit further into kind of an urban planning and design thinking, or cities could be imagined as if they were trees, and then you get the picture of London in which it's all broken down into little segments, and they don't really have much to do with each other. If you live in this neighborhood, you don't go to the other neighborhood, right? And some cities actually maybe work more like that than others, but in London it doesn't really work like that, as anyone who commutes knows. You go all over the place, and you go here for fun, you go there for shopping, you see different people on the train, you hardly ever see the same people on the train. So cities could be imagined as trees, but that's not probably what we want to do. Just as proofs could be imagined as trees, that's not what I'm going for. So now away from the urban planning pictures and into something a bit more like history of AI stuff. So in the history of AI, they built these computer systems that can manipulate blocks. They stack the blocks on top of each other. Some blocks stack better than others. Some are different colors, and so you can say move the green block on top of the red cylinder, or whatever. There's not a whole lot of reasoning there. Either the green block will go on top of the cylinder or it won't, right? So you check if it's consistent, but there's not a whole lot of reasoning there. Board games, as we recently learned, are more challenging, but yet solvable, sort of, by computational means. We haven't learned that a lot of it. We really learned it recently with AlphaGo. You've got your game pieces, you've got some rules and strategies, you've got a way to predict winning, that's the big piece of AlphaGo, and you have to decide between multiple strategies, right? Well, one thing I would say about this is, let's keep in mind that board games have this property where the meaningful representation is just the chess pieces or Go pieces on the board. There's this ability to build a meaningful representation is not so complicated. Stories are different. Stories relate to everyday life. And so you get kind of messy analogies and costs and benefits, ethical dilemmas. If you want, one of the research stories is you want to send a robot to a pharmacy to pick up a prescription. Okay, we have to tell it you can't kill the people in line just to get the prescription faster. That would violate your ethical premise of going there to get the prescription in the first place. So the claim is that mathematics is someplace in the middle between board games and stories. It's got all these nice, messy, real-world aspects, but there are also rules as well. The difference maybe is that we make up the rules on a kind of case-by-case basis, and then if we want to change them, we often can. So it's a bit messy someplace in the middle there, but we can be inspired by history on both sides. So relative to what I'm talking about today, there has been some other programming work. So Flare and Zigzag are classics. Atom Space is kind of the contemporary analog to what we're doing. It's more industrial strength than what we're doing. And then, as someone else was saying, you get more commitments, so you can't necessarily do the interesting, simple things that make all the commitments Atom Space. That's the practice side. The theory side, which I'll explain these emoticons and stuff, but we like inferencing theory and content, and I'll say what that is. My colleagues on this paper have invented that, so that's good. Conceptual dependence we like, that's something from the history of story understanding, that's good. Structured proofs I'm less excited about for the reasons I was kind of describing. They're trees, but I'll show you. In Lakatosh games I put this cat because I helped invent that, and I think it's great and stuff, but actually, it's not what we really want for this problem. So there's a cat. Okay, so inference anchoring theory plus content. This is what we use to model what people say when they talk about mathematics. So this is going to be a running example throughout the rest of the talk. What is the 500th digit of square root of 2 plus square root of 3 to the 2012? Eventually, this a computer will be able to solve. Can we do this for x plus y, for e rational to a small denominator? So what does it mean when we say, can we do this? It means compute the 500th digit of that thing, plug it in, or e to the 212. And so I've just kind of mapped out what he says. This is one person talking in a monologue. You can do the same thing with dialogue. It doesn't really matter if it's monologue or dialogue. There's all assert statements. And there's some markup going on inside. And these gray boxes are like, you could mark that up further, but that's the plus content stuff. So there was previously something called inference anchoring theory without the content, where you're just looking at what people say and you're looking at the logical relationships between those things. But in mathematics, you've got all this content. You're not seeing the links between the content here so much, but you see here things like this analogy. So this is proposed somehow in analogy with this. So this is not like, this doesn't follow from this doesn't refute that. It stands in analogy with this. And this thing is, who knows what to do with that, just to have a computer. So that's just kind of floating off on the side. But you got this intermediate structure of a graph, right? So that's what it is. Just modeling what people say. So remember on my first slide I said about representations that are meaningful. Well, it's a representation, but it's only meaningful if you think it's meaningful so far. So that's the start. So what is IATC? Here's the little sample of what it is. You can assert, agree, challenge, or track. Define, suggest, judge, query, or query extensionally. And you can say a bunch of different things in the middle. I've only put 3, but something as a property, something you can use a strategy on a certain statement, or maybe some statements used. These are things people say when they make mathematics. And there's a bunch of other things to say. So the language isn't like, here it is, we've decided now finally we're going to publish it in stone tablets. And we won't, we'll probably publish it in a Git repository or something less permanent. This is just the case. So here's conceptual dependence. This is something much more classic. So let's start with an example. Willow was hungry. She picked up the Michelin guide. Great. Why? She wasn't going to eat it. I don't think. So here's another example, which is less exciting. But John and Mary, they're doing something about a book. John is giving a book to Mary, but Mary is giving some money to John. And so somehow this other link here in the middle is saying, oh, giving the money to John is causal in John giving Mary the book. So actually, Mary's buying this book. So if you represent a bunch of stuff about the world, then you can reason, oh, she was hungry, she picked up the Michelin guide, because you need to find a restaurant, obviously, to get some food. And you need to reason about what goes on in the restaurant, et cetera, et cetera. So this is what you can do. And answering this why question is a kind of classic AI thing. So what if we use something like CD theory to build a system that could reason about why people say what they do when they talk about mathematics? Then the previous diagram I showed might actually be meaningful in the kind of computation. So that's that. Okay, structured proof. Remember the kind of not so smiley emoticon. Well, structured proofs are not bad. Here's a proof sketch of the 500 digit of this thing, even this, blah, 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 for n large enough, n small enough in comparison. So we do something that starts to look more formal, more like a tree. In fact, it is a tree. You've got 1, 1, 2, 1, 2, 2. This thing terminates in a little proof, so this is like a lemma. This thing here, can we compute the nth digit of this? 2 plus 3 to the n, not a bad idea. Why not try it? Let's in fact try it with n equal 2. Okay, n equals 2. We computed that. Well, but what's the nth digit of that? So this terminates with this star because who knows? Well, so this isn't even a valid proof sketch. This isn't a valid structure proof because you can't terminate with a star. It's not a proof at all. So it's not suitable for our purposes. You could write a proof of this theorem using a structured proof, but it wouldn't be written this way. So I'm just showing this to you because it's kind of a state-of-the-art sort of. Okay, so except this is the real thing. Lakatosh games is something we worked on, published this year in the Artificial Intelligence Journal. And this is like a behavior tree, so if you're interested in game programming, you probably use these things day in and day out. If you're a proponent, you can introduce a conjecture, then you can introduce some lemmas, and you can say, I'm done. After you're done, some opponent can say, hold on, you're not so done, here's this global counter. And then there's all these rules about what you can say after which move as you're arguing about the proof. So it's kind of like the chess game I was talking about. You push the bishop, okay, I'll look against my rook. That. Well, I'll take your rook. Okay, that's fine. That's great, all fine, but this isn't everything, because what's going on in this model is they're just arguing about examples and counterexamples, and they're sort of saying, oh, your counterexample isn't a real counterexample, it's a monster, let's get rid of it, and then you have to do all this kind of stuff. Eventually you get to surrender or accept. So this gives a skeleton for one kind of dialogue, and that's fine, and that's great, but that's not the whole world. So it's good, but not sufficient. So what we're really interested in is what Timothy Gowers called a quantum of progress. How do we get from step to step in these proofs, right? And they, so Timothy Gowers is famous for building a social experiment called Polymath, in which he said, make really small comments, just move it forward a little bit, that's the quantum of progress. But what is the quantum of progress? They also built this system called Robot 1, which is a mechanical prover system. It can be regarded as repeatedly applying a single tactic, which is itself constructed by taking a list of subsidiary tactics and applying the first one. So it's this waterfall model of coming up with a proof. You know, if you can apply this rule, do it. If you can't apply it, go on to the next one. And that works if you have a kind of simple thing. It's a lot like the system, or the logical system I just showed you about the dialogue. But compare that with this classic program Hacker, which isn't that good at solving blocks world problems as it would be if it was an expert system for solving blocks world problems. That's not what it is. It's a model of how learning takes place and how computational skill acquisition. It's a model of what it means to learn from experience. And so it's interesting in that regard. Could we have something similar in mathematics, which would be how you could use all this real world data and you have to learn from it. Okay, so let's go through this whole example a little bit. So I showed you a little part of this. I'm not going to probably do the whole proof for you, but well, I'll put in some highlights. So can we do this for x plus y for e? Right? Like you're given this, you probably think, how the heck could I do it? I'm stuck. Total stuckness can make you do desperate things. What does that actually mean? It means we're going to try to simplify so we can do something completely desperate. In fact, it should be really straightforward once we find the trick because it's a problem. So I'm expanding all these things, and some of them are suggestive styles. So can we do this for these things? And this, like all this unspoken stuff, yes, we can do it for rationals. In fact, which is going off the page. We'll progress down this general scroll, which is in the paper. How about small perturbations? Maybe it's close to rational. Okay, so this is suggesting strategy. Maybe it's close to something that we can compute. Here's this square root of 2 plus 3 to the n. Here's the square root of 2 plus 3 to the 2. So this expanded. Yes, we can really compute that, but it's not really a lemma. It's just some sketching on a chalkboard, right? There's that. And then, oh, here's the brilliant insight. Let's just get rid of those things that were annoying before. 4 by doing this and make it 10. Okay, so that's good. And this is just some mathematics here, working that out. Okay, this is the content level. This is the strategy is eliminate crosslinks. And then here's the really good insight. This thing is an integer, so we can remove all the crosslinks, all the ones with minus signs, have the exponents work out by this binomial theorem that they cancel. So everything with a minus sign cancels. Okay, that's because 2012 is easy. So there's the strategy which generalizes the other thing. We've still got this 10 over here floating on. So now this thing sums the sum integer. We don't know what it is. It contains this thing as a sum end. This thing has the property that it's small. Okay, and all this is expanded. So this is a very small number. Maybe the final answer is 9, which might seem a little bit shocking if you haven't thought about this proof a dozen times. But why would it be 9 for this small number? Well, I'll show you this in a minute. So let's just check if it's small enough. So then you do all this little chain of arithmetic. This thing is less than half. That's a good estimate. You do some little analysis here. None of this stuff, by the way, see all these asserts, very little of these things were actually done in the initial proof, but I expanded it out a bit more. Oh, by the way, I've got these arrows kind of pointing off in space. So I'll say more about that too in just a minute. So this thing specializes. Anyway, it's 9 because it's small enough that we've got, 502 zeros in the decimal expansion of the thing, so there's 503 nines in the thing that you subtract off. Okay, so the answer is 9. Okay, great. So that was the proof, and if you were all mathematicians, you'd say, oh wow, that's so great. Stop talking now, so let me check the proof. That's really but what about making this functional, like we were talking about before? So S expressions like these things, which kind of represent the arrows I had before, can be fed into a program called Arcana, building up a graph representation. And what about the reasoning? It takes us from step to step. So I want to give a little homage to these guys called the Oxford calculators who invented kinematics and dynamics. So these are like your kinematics. These are the things that people say. At some point, someone said this. Why? We don't know yet. Not quite. We're getting there. Oh, I want to point one thing here. This little pound or hashtag subgraph. I think it's pronounced hashtag now. Pound was back in the 80s. That was when I had this arrow pointing off to space. Really, you should think of that as drawing a lasso around some stuff. So I'm going to lasso that subgroup, and I will convince you that I'm very can lasso it on this slide. So list, you might have noticed, has something called console, and A.B, which you access as car and cooter. Arcana has a different structure, ACB, which is a source text. Text is the thing in the middle, and a sync. Depository of Nemus is a plexus. A0 is used to represent A. Someone here in the audience told me I should have A0A to represent A, but that's still under debate. But we're at least calling them polygraphs now. We used to call them isographs. So what is that? So here you've got your good old friends Jane and Jim. They got married, like in the song. John disapproves of the fact that they're married because John loves Jane and John likes Jim. But Mom resents the fact that John disapproves of the fact that Jane is married to Jim. This is what you can do with this kind of reified triples that you don't do with just normal, regular old triples, right? Because you can point at these edges. These edges are things. Someone could say, this edge is a thing. And when you do that, then you can point at these subgraphs like this triangle here, and that's where you get this lasso feature. You still have to draw all these extra edges, but at least you can say, yeah, I mean that triangle, and say not that triangle. So here are the key ideas in the proof, rendered as graphs. So why is it that 9 is the likely answer once we know that this thing is small? Well, we know that this thing is close to an integer. Okay? This thing here is close to an integer. And this suggests the property that it has 9s in its decimal place because we know that, right? So this thing is equal to an integer. This thing is close to an integer. We actually don't know, for example, if it's going to have 9s or maybe 0s or something, but it's suggesting. So what I wanted to point out about this, the reason I'm making a big deal about it, is we're doing something that's not strictly deductive, and we're doing that right in the middle of this proof, or right in the middle of the proof description. We're doing something kind of abductive. We know that when things are close to integers, they might have 9s in their decimal points. That's a theory. Now we've got to do some more work to check that theory. So we're doing this little abductive step right in the middle of our proof, which is different from how we are supposed to. So in the paper, there's a bunch of S expressions, and rather than reproducing them on the slides, which you couldn't read, I thought we would do something else with a big screen, which is just kind of show what those S expressions in listing 2 are. And this isn't a demo, sorry, but it is a pictorial, graphical kind of paper demo, if you will. So this thing is small, implements the this idea, this strategy. Numbers closed integers have 9s in their decimal expansion. So if we unfold that, this is the folded thing, which might have appeared in the graph, or maybe it didn't. Maybe we had a missing edge. I think this is what it says in the data. We had a missing edge, and actually these things should all connect with each other mostly because you're supposed to use the things you talked about in mathematics. So this is filling in an edge that wasn't in the original picture. And this is what's really going on, because like I told you, these are semantic networks. They're nested inside. So this implement is actually going to have a certificate computation inside. And this, number of closed integers have 9s in their decimal expansions. That's what this says. This is a little regular old semantic network, except this bit is circled. If n is close to n, and n is an integer, draw a circle around that, then that stuff implies that n has property minus decimal. Implies, doesn't necessarily prove. Okay, so here's this as that property small, and so these are the things we know. So, of course, that's not enough. We need to know that if n is a property that's small, it's equivalent to it being close to 0. We need to know maybe that 0 is an integer. If something's an integer, then it has a property that's computable. These are things that we know, but the computer won't know them by default. So we need this thing, which I personally call the hyperreal dictionary of mathematics, which has everything in it, just because we put it there. Actually, we're going to have to build that, but these are some of the things you could program. Okay, so you program that in, and then it's available, right? What else is available are some rules. If something has a property, and you've got implies, and you've got this box in the middle, you can just shrink that arrow directly down to a has property. You can kind of just eliminate this stuff in the middle. Or if P connects with X and X connects to Y, you can just slap those two things together, right? And then we can sort of say if something's equivalent to, then it can be wise, right? So here's some inference rules. And these are interesting because these are like graph grammar rules, right? So what you're really doing is you're looking at that big graph I had, possibly augmented with some other stuff, and you're saying, oh, well, we'll let that graph mutate, we'll let that graph evolve and change and kind of parse, or even sort of parse itself, adjust itself dynamically, as it were. And there it is, that good old certificate, right in the middle of the implies node, which is basically a lambda expression, that's what it says in the paper, where you chain all these things together in the right way. Proofs are still trees, like I told you, we still like trees, even after everything I said about them. So here's the certificate that proves, not the whole proof, but it just proves that the implements, that strategy that was suggested does in fact, or the little demonstration, the little lemma, does in fact implement the strategy that was suggested. So this is a certificate you get when you do that. But this is a caveat, because actually this is all constructed by hand. There's no higher order reasoning that's like under the hood. There's no magic that says, oh, I know how to prove the whole proof. And we're only looking at one step anyway, but the thing to emphasize here is that all this stuff is constructed by hand. If you wanted to have a real AI, the next level is put everything together in the correct way. So that's not been programmed. Okay, so future work, conclusions and future work. Well, so as I explained, we talked about the computational theory of this expository register, which is different from trees. We used some hypergraphs or polygraphs to do it. We drew upon contemporary argumentation theory and classic story understanding approaches in AI. And future work would integrate all these other themes, which we haven't done, including machine learning, but you need the representation in the first place to do machine learning. Extensions to the system are planned. So yeah, like you said, maybe eventually the computer will be able to step through the whole proof. And what would be really great, here's the motivating thing, is that why don't we get the computers to talk with each other so they can look at dialogues or texts or expository things online, and they can have dialogues. And then they can converse with each other to sharpen their wits. And so this is what Alan Turing was working on in the last years of his life. Of course, he's still working on it now. So unlike computers, people do die, so so if we get this done before there's a blue flag of money. I think his hand was up just a minute before you still kind of go back.
So thank you, this was particularly fascinating. Sure. I think there's obviously going to be a lot of interest in trying to understand mathematical thought processes and building towards this automated proof search, which is much more powerful. But another aspect occurred to me that the kind of practice of mathematical exposition is different from the process of discovery due to cultural factors. So people will do their work and it's embarrassing formal reasoning and things that don't quite make sense, but they somehow get to the right answer, and things written on dirty napkins and all this kind of stuff, and then like all the mistakes and things, and then that gets cleaned up, and a few mathematicians are different, but most people will then produce a logical exposition, which is like, seems to come from some kind of super powerful mentality that always chooses the right path, and here's the, look at me, I'm so smart. And only if you will kind of, let you into the private workings of their mind. But I guess this kind of puts that on like the actual process of thinking as kind of, that seems more reputable because you can't this one. So anyway, I wonder if,
yeah, so I would just comment that the proof here is a good example. It's called a magic leap problem, right? Like, how on earth did you get 9 with that thing? Why did you think you could use the binomial theorem? Why did you think to try e or x plus y? Those don't make any sense. But if you start to think about it and you know what happens, you see this transcript, you say, oh, this process where they're looking at x plus y and e and rational numbers, that was like an inductive logic step. Like, not induction in the mathematical sense, induction in the logical sense. We're saying, let's look at a bunch of examples and find the one that actually works. Rational work. Wow, after looking at these things. So now we've induced this thing that works. Now what else works? And so, so you're on this path. You say, now that I know something works, maybe it's close to rational. Maybe it's close to integer. Where could I get an integer? So once you've kind of formulated the strategy, then the deductive logic, actually the structured proof of this would be pretty simple once you had the idea. So the interesting part is coming up with the idea in the first place. And I guess that's the backstage part. Yeah, people present these things in the front stage as if they were done, finished pieces, but you don't see the production process, which is messy. And yeah, so we're interested in the backstage, or sometimes even the backstage of the backstage if people give us access to that.
and I suppose mathematical maturity is a like database of inference heuristics.
It could be, that would be, yeah, I mean, you have to believe each person has their own set of inference rules, their own set of patterns that they recognize and strategies and stuff. Okay, so, yeah.
So you mentioned Lakatos games, and that was the first I've heard of these, because I've been reading proofs and reputations, and I was wondering if you knew of any work that was sort of formalizing that book in Lakatos.
That is Lakatos games.
Yeah,
So yes, I know of work. It's my paper with other people, and that's where Lakatos games come from. So we tried to formalize the ideas of that book. So it's in AIJ and May this year.
Okay, and I guess Lakatos starts the book with sort of this diatribe against formalism.
Oh yes, he does do that, right? Yeah.
So I feel as though, like, do you ever feel as this is like sort of against that sort of philosophy?
Yeah, that's a good question. It is a bit odd. So what we've done with Lakatos games is formalize his informal logic. So we haven't formalized really the process of doing mathematics, but yeah, that's a pretty deep question. Am I in favor of it or against it? Well, I would say there's two things. In this paper, we talked about something called flexi-formalism, which is basically, it's not black and white. Things aren't necessarily formal or not. You can have something in between, right? And formal in mathematics usually means strict deductive. So I'm basically not interested in that because there's other people who are much better at formalizing things in that way than I am. But I am interested in computational systems and understanding how they work and making things that are useful, say for computer tutoring or whatever. And I think that that's where you do something else. It's not formalism in the mathematics sense, it's in the AI sense or something. So I don't think it's not in the spirit of Lakatos, but he's not around to argue, so I guess we're going to just go with it for now. But at the same time, as you saw, there's a cat smiley face there, not a normal, actually a cat smirk face. It's not like I love that and I think this is the way to go. I think the way to go is much less formal and much more heterogeneous, using lots of messy real-world data. So again, I think that is in the spirit of Lakatos, if not in the letter.
So in the ICFP community, and I, as an example, we, formalize things as a way of getting our thinking more clear sometimes, and are in the practice of doing mechanized meta theory. And I've personally found this to be a tool, when I'm working on my own, maybe I don't really understand the problem until I start to try to formalize it and work with a computational system to see if it makes any sense. And also in the process of sort of social mathematics, like if I know that somebody else uses the same automated proof system that I do, or the same interactive peer prover, I'd like to have a conversation with them that's more precise and where we can make progress faster because we can formalize things in the same way. So I'm just wondering, you know, do you have any optimism around some kind of accounting for the social process of mathematics being compatible with that style?
Yes, that's in another paper in preparation for AIJ. It hasn't even been written yet, much less submitted. But what my main job is to study the social machine or social machines of mathematics. And all of this stuff is kind of like a depth-first search down one part of the social machines of mathematics. But another big part is talking with people who use proof systems, understanding why did formal proof catch on in the POPL community, for example, and not in some other HCI community, for example, or the theory, I suppose, caught on. Yeah, I think when it's kind of quasi-formalizing what you were just talking about, what we really need is a proof system here. You're right, that's obvious. Why didn't we think of that before? Had we had this proof system, then we could have saved ourselves weeks of Haskell or something like that. So, but figuring out what would make the social machines of mathematics work better is a big question. So one of the things I was interested in is like, you've got these Stack Overflows and Math Overflow things. Like, why am I interested in AI? We've got this human-powered thing that works great. People pose questions, other people answer them. What's there to complain about? So it's tricky to make a case about why would you need some more computational system. But I think things like what you were saying, it gives you something else to talk about. You look at where did it go wrong. Whereas if you ask the question, someone says, this is a dumb question, you don't really know. Were they being biased or was it really a dumb question? That so you can debug further. I don't know if there's any question.
And one more.
Yeah.
On the slide you had with the CD diagram, you had something like a graph representing somebody buying a book.
Yeah.
And had this transaction where this guy gets a book from this person and also the other person receives some money.
Yeah.
And there wasn't a formalization there of sort of ordering. One way to think about it is, you talked about how it's sort of cause and effect, and how by giving them money you get a book, so you put that cause and effect relationship in. And indeed in your proof it seems like ordering was just like this giant thing that you needed to drive the whole sort of implication. I was just wondering if there was more to say about the sort of maybe meta theory of ordering or something like that.
Well, so first back to that diagram. That we sort of made that up. Like that diagram wasn't quoted. That was an original diagram trying to interpret how does this CD theory work. We have to try to ask the people who made it. Does it really work like that, or is there a different way to show these links between links? Because links between links is very much the kind of thing that we're doing here all the time. But there's got to be something like that, some way to represent these complex relationships. And I just couldn't find a picture from the old papers that had that. So let's just have that caveat. But in terms of causality or ordering, this is what I said at the end. This was the caveat at the end. It's like, we put together this lambda expression that gives you a proof, but how did we know to put together that lambda expression as opposed to some other one? Are we going to try every single lambda expression until we get one that works? That sounds like a bad plan. So the heuristics would be, heuristics means search, right? So how can we search the whole space of possible lambda expressions without getting lost in it, and put things in order that way? So it remains, that's a focal question for the next round of work, I think. I hope I don't really look terribly satisfied with my answer, but I think it's
Hume had the same problem, right?
Okay.
Bus thing, right? The story is you come to this world and you don't know anything about how anything works, and you see somebody flag down a bus and it stops, and then the natural deduction there is that them waving their hand around actually caused the bus to stop.
Yeah.
Perhaps it's not really something that can be formalized.
Yeah, so I guess I would just say in the mathematics world, you don't have to necessarily worry too much about causality. That was in the CD thing you do, the story. But with mathematics, I think you just have to worry about did the proof work. So it's I'm not saying that it's not a concern. I think it's an interesting question. But you do have this kind of ground truth, which is, okay, I pick my axioms, I pick my inference rules. It seems to work, so.
Yeah. Thanks.
Thanks, Joe.